Morning everyone. So some of you noticed that SetU is now available. Now a lot of you haven't done SetU before. It's Student Evaluation of Teaching and Units. It's an important part of feedback that we'd like you to participate in, particularly if it's positive feedback. So there's a few things. It's very easy to do and there's prizes on offer. There's $50 book vouchers if you are lucky. I think there's quite a few of those, but I don't know what the probability is. You'll have to work that out yourselves. It also helps us with our improvement of teaching and understanding what you think needs improvement or you think is good. We don't want to remove things that are good. We want to add things that are improving things. Okay, so it's easy to do, so why don't you do it? So there's some examples here. So students may request more details about their assignments, different activity times and perhaps better guidelines in their final exam, although the SetU is due before the final exam, so that's a bit of an odd one. You might look at previous exams and think, oh, that's a bit hard to understand, so that might be some feedback. And we can respond by, of course, improving those things. We might add extra practice exams. And in this unit, we actually go through the solutions of previous exams, and you'll find all the lecture videos for those for previous years as well. So at the university level, we like to keep track of quality. So that will improve staff promotions, for example, and also appointments in the future. And I'm the Director of Teaching and Learning in our department, so I'm particularly keen for feedback from students to improve things. We have a prize night tonight, if any of you want to go along and see our best students. We award prizes for the top students in various categories. They're money prizes as well. You can get a little bit of a boost financially. So you just go into Moodle and you'll see a link through to the survey. You can do it on your phone. You can stop halfway through and save your responses and resume it. So they've improved SetU through feedback from students as well. It is confidential unless you're extremely abusive, and then they'll go to all lengths to track down who you are, but they don't do that unless there's a serious issue. But don't say who you are in the comments because they're not redacted at all. So they come through and we'll see the comments as you write them. They used to censor them. They used to remove ugly words, but then they ended up changing everything so we got no feedback pretty much because they got a bit sensitive. So anyway, they don't remove anything these days. And if you want to see how other units go, you can look that up in previous years. So it's transparent to you as well. All right, so get on with it, and we like the high participation rate. Yeah. All right, any questions on SetU? So when you're bored in lectures, you can even do it as well. But then it won't be a positive feedback experience, I'm sure. Okay, so today we're going to continue our fixed point arithmetic. This is a very important topic. So today you're going to learn how to apply this to real-world problems, particularly the pendulum project, which is an example you're working on. So we introduced this last time where we're basically talking about integer operations, addition, subtraction, division. And in integer operations, the hardware is quite simple compared to floating point. So you'll find a lot of processors, microprocessors, particularly low-end ones, will not support floating point because it makes the chip much larger if you include that and slower. So we should really know how to work with integer arithmetic to represent real numbers as an approximation, so rational numbers. So you can do that by adding fractional bits. So this format we're showing here includes f fractional bits, so they're the lower order bits, f of them, and then there's integer bits which we denote with an I, they're the upper order bits. So you might have 10 integer bits, so they're the 10 most significant bits of your integer representation, and you might have 6 fractional bits. So given 6 fractional bits, you can resolve to by convention, you're just adopting a convention in your understanding what a variable means. It's just saying, okay, the units are representing 2 to the minus 6 in that example, or 1/64th of the integer units. So you might be representing a quantity in metres, and you're saying, okay, we're going to resolve to 1/64th of a metre with that representation. Okay, so as you know, you then want to do some calculations, and it's important to understand how that representation propagates as you do multiplication, addition and subtraction. And we'll also look at the effects that we can achieve through rounding, which is an important thing related to errors that you come out with. So integer representation with just f fractional bits is an approximation. So you've got to understand what the errors are in that approximation, and that's something that's important. And we'll show you how to improve something that you've already used in the operating system, which is the utilisation percentage. Okay, so in multiplication, we've already looked at addition and subtraction where we just match the number of fractional bits. So you may have to do some shifting to do that. If you're adding something with 4 fractional bits to something with 2, you must shift the 2 to the left 2 bits to make sure it has the same number of fractional bits in that case. Multiplication, we don't have to actually match the number of fractional bits. So when you do multiply 2 numbers, you're going to add the 2 fractional bits and add the 2 integer parts. So in this special case of I point f, you end up with 2 integer bits times 2 times the original and 2 times the fractional. So you're adding in when you multiply 2 16-bit numbers, you get a 32-bit result. So you're actually adding the number of bits in the operand to the result. So if you think about that, that 2f is resulting in a higher resolution. It's 2 to the minus f, 2 to the minus 2f. In the result. So this is a symbolic representation of what we're doing. So we're multiplying x by y, where x is I integer bits with f fractional bits. And it's likewise with y. So when you multiply those two together, you end up with 2i and 2f fractional bits. So if you want to represent that result in terms of the final I.f that you started with, you need to start pruning bits. So you take off f bits from the right-hand side, and likewise I bits from the left-hand side. But when you do that, of course, you are removing information potentially. So if you start pruning bits, then that creates an error. So let's try and understand what that error is. It's clearly just subtracting that quantity in the lower f bits. So once we do that, we'd like to make the error as small as possible, and we can achieve that through what's called rounding. So rounding will pick the nearest result to the real result in the representation we have. So if it's close to you might have a number, 1.7, and you want to round that to the nearest integer, you obviously go up to 2 in that case. So you pick the nearest integer going up or down. 1.5 is problematic because you can go either way. So in the case we're looking at, we're going to choose to round upwards when it's equal spacing between the two representations. Okay, but you'll probably know from your other work that if you have a digital signal processing chip, that they can actually round up and down, excuse me, alternatively to get an unbiased rounding. We won't discuss that today. You can look that up. So how do we do the rounding? Well, if you want to convert from 2i dot 2f, we can do that by taking our result, which is in that format, and we add 1 shifted left f minus 1 bits. Okay, so that's representing a half now in this format of the result. And then once you do a shift to remove the bottom f bits, this effectively becomes half of the lowest bit beyond where we remove it. So the most significant of the f bits we remove, we're actually adding a 1 to that bit using this 1 shifted left f minus 1 in this result. So the effect of that is adding a half. Okay, once you think about 1 bit beyond, that's a half of what we're dealing with in terms of the integer. So once we do that and then we chop off the result, we're truncating after we add a half, which is all looking very complicated in this expression, but once you keep track of the number of bits, you can see that is in fact what's happening. I encourage you to do examples with this stuff later on. Just trot out some numerical examples and work through what all this means if you're having trouble understanding it. We'll look at some examples too as we go through. The other issue that can happen is due to the sign bit. If you've got a negative representation possible, so if you have a signed or 2's complement representation as we call it, the most significant bit on the left is the sign bit. And as you know, the representation for minus n, we'll call it minus k actually. If you have a number k, might be 10, and you want to represent minus 10, then the way that's done in 2's complement is you take 2 to the n minus k. So you convert that to a positive number effectively by adding 2 to the n to that, where n is the number of bits in the representation. It might be 16 bits. So what happens with 1, for example, is you end up going for 2 to the, say, 16 minus 1, and that produces all 1s, okay? So what can happen is if you start pruning bits at the top level, if you're looking at minus 1, so it might be in 4 bits, and you want to convert that to 2 bits, well, you're just going to remove the top 2 bits. And if they're all 1s, then it's actually not a problem. You end up with the correct result. Minus 1 in 2 bits is 1, 1. That's fine. But if we happen to want to convert a number which had a 0 amongst those bits we're going to remove, you'd get the same result here. And you know that if clearly is not minus 1, to find out what that number is, we can do what's called a 2's complement operation, where you complement the bits and you add 1. So that gives us 5. So we know this number is representing minus 5. Okay? So minus 5 in 4-bit representation is 1011, and if we convert that to 2 bits by just truncating the top 2 bits, you end up with minus 1, which is clearly wrong. But you can't represent minus 5 in 2 bits. It just doesn't fit. Okay, so just be aware that if you are pruning the top bits in a sign representation, they must all be the same, otherwise you're generating an error. So in the case we just looked at, we get a 0 amongst the 1, but if you had, say, 0, 0, 1, 1, and you want to convert that through, again, you'll note that you end up with 1, 1, which is minus 1. So you actually have to consider these bits have to be equal to the final sign bit for there to be no overflow, okay? So they're all got to be the same in the top 3 positions in this case for that to work out correctly. All right, so that's a little bit technical, but I'm sure you can see the issues involved in converting. So another way to look at this is if you get a result outside the allowed range of our 2's complement representation, you know there's an overflow that will happen. So for example, in 8-bit 2's complement, you know you can go from minus 128 to plus 127. So that's minus 2 to the n minus 1, where n is the number of bits up to 2 to the n minus 1 minus 1. That's the range for 2's complement. If the result is, say, minus 129, of course you're going to get an overflow in that situation. All right, so if we're talking about unsigned, however, it's much simpler. So if we truncate the upper bits and any one of those bits is a 1, then clearly you're going to get an overflow situation. All right, so here are some examples. You should be able to do these, but we won't slow everyone down by doing them. So let's just ask a few people a few questions. If you're doing this in 2.2 format, what's the resolution in the fractional bits of 2.2 format? So we might be measuring metres, and we say, OK, we want to measure up to 3 metres, and we're going to use 2.2 format. So what fraction of a metre are we resolving to in this format? Can anyone tell me? Just to check you following this. Is it half a metre, quarter of a metre, or an eighth of a metre? Okay, let's do an example. All right, if we had the number 10.01, what would that represent if we're talking about metres, distance, metres, SI unit of distance? So the integer part is 2. And the fractional part is 1, but what's the resolution of the fractional part? So what's the weighting of this bit? 2 to the power negative 1, thank you. So that's a half, 2 to the minus 1, and this guy's got a weighting of 2 to the minus 2. So the result is we have 2 and a quarter. All right, so 2 to the minus 2 is a quarter. So that's the resolution is 1/4 of a metre in that case. All right, so you know now, maybe you know that you can represent 1.75 as 01.11. All right, that's 3/4 of a metre. And we're multiplying that by 01.10, that's 0.5. So these are decimal, obviously, the representations here, and these are binary up the top. So if you do that multiplication, we're actually, in integer arithmetic, that's the same as multiplying 7 by 6. So you end up with a result of 42. But in binary, you need to do that as a binary number. So 42 is 10 plus 32, which is 10. Yeah, 10, 10, 10. So we know the result there. We've got 2 fractional bits here, so we have to put the fractional point in here. It's a little bit hard to squeeze that in. So we end up with the result 10.1010, but we're going to truncate that back in 2.2 in this example. All right, so here are the details. Oops. Just as I said, you get 101010, so that's 2.625 because we're now resolving to 1/16 to the minus 1, 2, 3, 4. Okay, so that's 16ths, and we've got 10/16ths of our fractional part. Okay. And if you look at this now, we want to convert this to 2.2, so we've got an option. We can do it with no rounding where we just remove the bottom bits, and you end up with 1010.10, which of course is 2, and then you just got a 0.5 remaining there. And the real result should be 2.625. So that's obviously an approximation, but if you implement rounding, what we do is we add the result shifted to the right 2 bits, so this 1, 0, and that's representing a half, so you're actually adding 1 in this position here. So we're going to add 1, 0 to that. Which then means we're going to round up in this case. So we end up with a result of 1011 in that result. Okay, so that ended up rounding up. As I said earlier, 0.5 rounds up to the next integer with this technique. Okay, so let's try the result now using 2.2 inputs and a 2.2 result. So that's similar, but we're going to do the conversion before we do the multiplication. So we do the result here, and then we remove this bit here. 2.2 is a little bit a problem in the integer domain here because we're actually removing a 1 in that result. These are unsigned representations, so you're actually generating an error here. So the result is, once we get down to 2.2, we're going to remove the bottom bits as well. You get the result of 0, which is obviously an overflow result, because we don't have sufficient bits to represent the result correctly in the multiplication. That's okay, so let's look at division now. Division is a little bit more complicated because we have this issue with the remainder. So if you do integer division, so you might do, for example, 11 divided by 5. What's the result of that? If you wrote in C programming, have a variable x, which is equal to 11, and another one y equal to 5, and you do x/y, x/y, what's the result? So this is integer division. Does anyone know? The answer is 2, isn't it? So in other words, we're just ignoring the remainder of 1 in this case after division. So C programming just throws away the remainder and then does no rounding at all. It does truncation. All right, so if we have a general case of I with F1 fractional bits and a different number of fractional bits we're dividing by, so these result in the quotient then has a resolution of F1 fractional bits divided by F2. So if you look at the lowest order bit, what it represents, it's 2 to the minus F1 divided by 2 to the minus F2. So you're actually subtracting F1 minus F2 in that result. when you do that division. So the quotient then has a reduced number of fractional bits, just due to this division operation. Okay, so we're going to deal with the fact that we're losing now precision or resolution in those fractional bits, and you do that by arranging the numbers before you do the division. So if we want to achieve f fractional bits from two input numbers, one divided by the other with the same number of fractional bits, what we need to do is to double the number of fractional bits of the number we're going to divide by the other number. So that's the dividend. So we've got to add extra fractional bits here, and then when we subtract f from the division, we should end up with f. So we've got to add f zeros on the end of the dividend, this number here. So we can do that very simply in C programming just by shifting left f bits, and that creates zeros on the bottom f bits. So that gives us I dot 2f, and then we divide by I dot f, and you end up with f fractional bits. So that's how you would write that in a C programming context. So these 0 bits are like when you do long division by hand, you're adding zeros in decimal to get the extra fractional bits. You'd probably done this in primary school when you were doing long division. All right, so that's what you need to do in order to handle the division. As you know, though, as we discussed, you end up with an error due to the fact you throw away the remainder. So let's try and work out what the best strategy there is with regard to the remainder. So if you are dividing by 10 and you get a remainder of 6 and you throw that away, you're actually truncating to a result that's further away from what we could have achieved. So let's have a look at, say, 13 divided by 5 in C programming would give us a result of 2. But we know the result should be 2.6. So you'd prefer to have a result that's closer to 2.6, which is 3, than just truncating and getting 2. All right, so let's look at what we call rounding in division to achieve the nearest integer result of the division rather than truncating to find the integer below the result. All right, so we really want that to be a 3. So how do we do that? Well, the way we do it in practice is we add a half to the result, and we add that up and we get 3.1. And then we truncate. So we end up with 3. So if we actually cross the next integer boundary by adding a half, you know you are closer to that boundary in the first place. So in C programming, you would take our dividend, we shift that to the left f bits as we did before, and we're dividing by the denominator. So we're going to actually add half the denominator in first before we do the division. So that results in a half effectively in the end result that we're adding on, and due to the truncation property, then we end up with rounding. So that's one strategy which is simple to implement, where this is representing our half that we add on. So this can be done in a slightly simpler way, but it looks more complex. But in C programming, it would execute potentially a little bit faster because we don't have to pre-compute the denominator. So we can do that by just starting with our I.f, but we're going to shift to the left f plus 1 bits, an extra bit to the left. We're going to divide by our I.f, so now the result has f plus 1 fractional bits because we shifted an extra bit left. So this 1 here is in the integer domain. We're adding a 1 at the end there. That's actually representing a half, okay, because we've got that extra bit. And then to compensate from the f plus 1, we then do a shift to the right 1 bit. So you then truncate that bit. All right, so it's like this case that we did where we had the addition with 3.1 and then we threw away the bottom bit. So you end up with the 3 in the answer. So as you can see here, we're just doing shift operations, a division, adding 1, which is an increment, very simple. A single instruction does that, and then a shift right 1 bit. But most people don't use this form because it looks complicated, even though the resultant operations are very simple. So here's a symbolic representation, by the way, of what we're doing here. We add f plus 1 fractional bits. We do our division in integer arithmetic. And at the end, we add 1, and then we throw away the bottom bit here, so we're then restricted to f bits in the result. It's a good idea to draw pictures of these things when you're working through what's going on. These sort of pictures here. All right, so let's have a look at what actually happens and why this rounding actually works. It all comes back to Euclid. So in terms of Euclidean division, there's a greatest common factor algorithm that's called Euclid's algorithm that is based on this approach. It was developed by the ancient Greeks. It's pretty smart and it's simple. So what we're doing here is called integer division. So Q is our quotient and we're dividing x by y, but in integer arithmetic. So that's known as the div operation in some programming languages such as Pascal. So in C it's just denoted by the slash operator that you're used to. Has anyone programmed in Pascal? No? But in mathematics they also call it div as well. So what we do is we say, okay, x is uniquely divisible by y q times with a remainder r, where q and r are unique. There's no choice there. They're uniquely determined. And we know r is between 0 and y minus 1. So that's the remainder. We've set that up so the remainder is always less than y in the division. So this, when we divide through this equation by y in our real number system, so x on y is now a infinite number of precision decimal number, if you like, or a real number. So you get x on y, which is what we were trying to achieve in the first place, is q, which is our result that we get from integer arithmetic, plus an error, which is r on y. So that error range is between 0 and 1 minus 1 on y if you do the division in proper division, not integer division. So we're approximating our real number, the real number x on y with a result that has an error range which is biased actually. So the error is always positive. You never get a negative error with this result, and the error range goes from 0 to just short of 1. And if these were uniformly distributed, so you just had a random set of numbers and they just fall equally on every number, then you've got this distribution that goes from 0 up to 1 minus 1 on y, and you know the average of that distribution, or mean of that distribution, is half of the maximum, which is a half minus 1 on 2y, half of this guy. So that tells us that we have a truncated integer division has a mean or average error of a half minus 1 on 2y. It's very close to a half, but not quite. And the maximum error is almost 1. So that's a biased error. It's not a good result. So we'd like to round that to the nearest integer which is unbiased. Alright, so the real number x on y, we want to find the nearest integer that's as close as we can get to x on y. And that's done through this rounding process that I mentioned earlier. X on y plus a half truncated is that result. So if the number's closer to the upper integer, adding a half will put it over that upper integer, and then you truncate it back to the integer below that. So it rounds up in that case. So that's approximated in C programming now by x plus the denominator y shifted one bit to the right, so that's y divided by 2 approximately. If y happened to be odd, it's slightly less than half of y because you're shifting out of 1, and then you do the division by y. Alright, so let's, we don't have to do this, but it's worth looking at this a little bit more rigorously. So if we look at the quotient from rounding QR, then that's what we just described. It's x plus y div 2, that's the shift to the right precisely now, and then the result of that all div y, where div is this integer division. So let's analyse that. So QR is then this, and we can decompose x as equal to qy plus r, as we did earlier. But now we're adding in y div 2, and then we divide by y. But we do know the remainder here is between 0 up, from 0 up to y minus 1. So let's look at different properties of r plus y div 2. This is the mathematical trick. So what we know is if r plus y div 2 is less than y, we're not going to round up actually. So if you look at this guy, we know that this is obviously a multiple of y, so when we divide by y, it's going to be perfect. So the bit left over, y, from that is r plus y div 2. And if that's less than y, we know we're not going to click over to the next integer because the remainder is going to be less than y. So that's this case here. So the remainder after division by y is this guy here. And if that's less than y, well, what happens? Well, we know that result QR is equal to Q because this guy doesn't click over to the next multiple of y. And then the maximum error is R on y. In x on y. So we know that already. We've already dealt with it. So if we substitute, we take this equation here, and we solve for r, you get y minus y div 2, and we're going to substitute that in here for r. So we get r on y is less, because there's a less here, y minus y div 2, we just substituted for r there. But you know y on y is 1, obviously, and we're subtracting from 1 y div 2 on y. Y div 2 is approximately half of y, so we end up with a half there. So isn't that wonderful? We know the maximum error in that case is less than a half. Now, what about the other case where if we look at this bit here, r plus y div 2, if that's bigger than y or equal to y, we're going to click over to the next integer up. So that gives us QR is Q plus 1, all right, because we've clicked higher over the threshold for the div y. So when you do that, you can do the same process. X on y is Q plus R on y. We know that already. And we're going to substitute now for Q here. So Q is equal to QR minus 1. QR minus 1. And we've got the R on y coming through. That's fine. So then we get the error So this is the error, is r on y minus 1. So we substitute for r, and we rewrite that in terms of y minus y div 2 because we know r is from this, this equation here, we know that r is greater than or equal to y minus y div 2. So we substitute that in and it becomes greater than or equal, and that we're subtracting 1 if you work that through, and you end up with minus a half. Okay. So it's sort of a proof for what we already knew. So in other words, if you summarise those two things, you know the error is between minus a half and plus a half, and it's unbiased, approximately. Okay, so our error range is minus y div 2 up to 1 minus y div 2 on y. So when y is even, we have an error range of minus a half up to just slightly less than 0.5. And the average error then is a very small number, minus 1 on 2y. It's a very, very small biased error, and that bias is due to the fact that the exact half will round up. Okay, we discussed that earlier. However, when y is odd, it's perfectly symmetric. You go from minus k on 2k plus 1 to up to plus k. So that's an error with a zero bias. Fantastic result. So in summary, if you round, you halve the errors and you remove the bias, approximately. Right, how are we going for time? Still got time. Okay, so let's look at our example of CPU usage that you all used in the lab. So this was done with integer arithmetic, and this is the calculation. We calculate the OS counter idle max. We divide that by 100 using integer arithmetic, and we're going to call that the denominator. Then on every second, we're going to calculate the usage as 100 minus the current idle counter, and then we divide that by the denominator. And that's the calculation. Very simple, but it could be improved. So let's look at how we improve this. So what are we going to do? We're going to implement rounding in these divisions. So here is the improvement. So we take our OS idle counter max, which you calculated from 1 second with no other processes running. Now we're going to divide by 100, so we add in 50 before we do that to add that half before we truncate. So that is now rounded and has approximately down to the 100th of a percentage point. That's approximately unbiased. And the CPU usage you can now calculate using this updated denominator. But we do another division here. We've got OS idle counter divided by the denominator, so we can then add half of that denominator on to do rounding of that division as well. So what's the net effect of all this? So let's try and analyse what we've actually achieved here. So if we look at the operating system implementation that you're using, it has the maximum error in the denominator is, which you remember is the max divided by 100. The maximum error is 0.99 as a ratio, and the mean error is 0.5. So in other words, the error could be 0.99, so you might truncate from a result that's almost to the next 1%, but you go all the way back down to the current integer value. So the average error is 0.5%. So you get a 0.5% bias in that result. So in terms of the final result, you can get a result, an error close to 1% in the denominator. Okay, so that gives rise to a factor of 0.99 of error in the denominator, and then your final division here is scaled by that factor. So in the worst case, you get an error of approximately 1 with this other component, which is very small. All right, so the average error is -0.5 plus the effect of this denominator calculation. All right, so what about our improved version, which is shown here, which would execute in almost the same amount of time because you're just doing an extra add and a shift. So the maximum denominator error is now 0.5 when you divide by that 100 with an average error of 1/200. So that's extremely small. It's less than 0.5% of that denominator error. And then the final absolute error is 0.5, and then you've got the scaling in the denominator error. And the mean is almost 0 in this case. So we've halved the error in the calculation, and we're still using integer arithmetic in this result. So let's summarise this quickly. So what have you learnt here? Well, you've learnt how you can represent rational numbers approximately using fixed point integer arithmetic, which runs much faster on a processor. So with f fractional bits, you're resolving to 2 to the minus f in terms of your units that you're adopting. So you can use addition as long as you match the number of fractional bits, same with subtraction. Multiplication, you're going to add the fractional bits in the result, so you may have to prune that back. Division, you're going to subtract the fractional bits, so you've got to pre-add onto the dividend before you do the divisor calculation. So rounding you achieve in division by adding half the lowest bit effectively. But you do that in tricky ways by adding half the denominator before you do the division. Or you can do it with the shift and add approach. Be aware that, of course, you can round when you do conversion from a high resolution to a lower resolution in the number of fractional bits. Again, you must pre-add a half of the lowest bit you're converting into before you do truncation. And we've shown an example of how you may analyse the errors of doing that, which is important. All right, so in the pendulum lab, we're actually using this stuff quite extensively in the PID control work, which is coming up. All right, so we'll just briefly introduce that today, and then we'll continue this tomorrow. So proportional plus integral plus differential control is pervasive. Most controllers will use this approach. So what is control? It's where you have feedback from a measurement and you're trying to control a variable in the system from that measurement. So you want to control it to be a certain value from reading a measurement device. And you want to do this continuously as you progress in time. So ideally you want to follow your desired trajectory. It might be an oscillation of a pendulum. You want to follow that as closely as you can by monitoring the error and feeding back to the motor voltage, for example. So what we'd like to do is to understand how to set the gain parameters and what it means to sample this in discrete time. Because in practice you really want it sampled continuously, but in practice you have to do it only every so often in discrete segments. So in the lab you need to tune and implement this stuff and work out what the errors are. So it turns out PID control is not only the most common, but it's the simplest controller that you can use typically in an embedded system. And when you say simple, you can actually simplify it by removing the I and D and just have proportional control, but we classify that as part of PID. It's a very robust solution. It can tolerate errors in the system and it's easy to calculate. So this is ideal for a real-time system. So what are the actual definitions we're doing here? So you need to understand what we wish to control. We're going to call that x of t. Now in the case of the pendulum lab, what do you think x of t is? The angle of the disc, that's right. So you're trying to control the angle of the disc to some desired trajectory, which is actually simple harmonic motion of the pendulum. And what's our input here? What are we going to control that with? What's the input? The voltage on the motor, all right? So that's through a PWM system, but it's the voltage effectively. All right, so you must understand these things very well. So we have the angle controlled by the voltage. Now we define an error, which is the difference between where we'd like to be, x star, and where we really are as x. So we might get that wrong, we usually do, and the error is the difference. Okay, so once you have the error, you can then define a new voltage by multiplying that error by a constant, k, p, proportional. And we can also integrate the error. We can add up all the previous errors, effectively. Integrate them, and again multiply by a scaling. And we can look at how the error is moving with respect to time, the derivative with respect to time of the error. Is it increasing or decreasing? Again, you can do that with a k value. So next time we're going to describe how you actually set this up and how well does it perform with different parameters for the gains. But we've run out of time today. So we'll stop there, and I will see you in the lab. And make sure you fill out your set use.
So in very long, if we do like 0 minus a value, is it going to be 2 complementary to the value effectively?
So you can define a signed signal in Verilog.
Yep.
The default's unsigned, but if you do 0 minus something, it'll convert from signed to unsigned for your result. It'll just copy it across, actually, it's just the bits.
Oh.
So if you do want it to work in signed arithmetic, you should declare the signal as signed. So you say y sine blah 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 x, or whatever it is, the number of bits.
Okay. So you said about something with the, if you want to truncate the magnitude
Yes.
out of the value,
Yep.
you can simply just do 0 minus the data.
Yep, so that's good.
So what are we effectively doing here?
So that's conditional, there's a question mark.
Yeah.
So if the sign bit's 1, we do the 0 minus the data. Otherwise we don't.
Yeah, so 0 minus data effectively converts it into